But what I want to do is I want to go back and think about that original characterization of U45 as an internal direct product. We haven't had as much opportunity to talk about internal direct products in class. You can see a lot about it in this week's videos. But I want to come back because this is something that you did on the last group assignment that I want to use as leverage to take the next step into the next thing that we need to talk about.
Some of us were not here for that.
Some of you might not have been here for it either, yeah. So U5, internal direct product U9. So what do I mean by that? What I mean is that this is a group that's capable of forming its own internal multiplication table, its own times table. It can be explained as the products of elements taken from a pair of normal subgroups. So here's what that looks like. So this is the diagram that should be familiar from your last group assignment. Is that we have one normal subgroup of U45, which is isomorphic to U5. So let me write that one in here. So that's this normal subgroup. And this is going to be, sorry, my pencil died on me here. This is going to be isomorphic to U5. And the way we find the elements in this normal subgroup is that they are all of the elements which are congruent to 1 mod 9. So starting with 1, I'm going to start by counting up by 9s and taking every element that I find in U45 that I get by skip counting by 9s. So from 1, I would go 1 plus 9, which is 10, but that's not an element. So I'll do 10 plus 9, that's 19. Okay, great, I've got 19. If I add 9 again, I get 28. And that belongs in my group, so it becomes an element in this subgroup. 28 plus 9 gives me 37. That belongs in my group also. 37 plus 9 gives me 46, but that's not an element in my group. In fact, it's equal to 1, right? So all 4 of these elements as a subgroup of U45 is isomorphic to U5. So on the one hand, we have that normal subgroup. On the other hand, we have a second normal subgroup. And because it's a subgroup, it has to include the number 1. Right? So I'm going to sort of write it as though it's going in this other direction here. And this other normal subgroup is going to be isomorphic to U9. Kind of draw it going down this way here. Isomorphic to U9. And we can find that by skip counting by 5s, starting at 1. So 1 is an element. If I go up by 5, I get 6, which is not an element. If I go up by 5 again, I get 11, which is. I go up by 5 again, I get 16, which belongs. I go up by 5 to 21, which doesn't. 5 again gets me to 26, which is. 5 again gets me to 31, which belongs. 5 again gets me to 36, which doesn't belong. 5 again gets me to 42, which doesn't belong. And then 5, wait a minute. 41 is there. But then 41 plus 5 again is 46, which takes me back to 1. So here in purple is another subgroup of U45, which is isomorphic to U9. It has 6 elements in it, just like U9 does. And so what's great about this, and this is what your last group assignment looked like, is that if we take the products of the elements in the first row and the first column in this table, we're going to account for all of the other elements inside of U45. So for example, 19 times 11 would be 201, is that right? But mod 45, that's equal to 31. Yes. No. Wait. It's equal to 29. And so on and so on. So we should probably use technology to fill out the rest of this table. But I'm running a little bit short on time. So what I'm saying is that this group has sort of 2 different kinds of tables that we can use to represent its group operation. We could just write a Cayley table for U45. And if I wrote a Cayley table, it would be 24 rows and 24 columns. So there'd be 678, 578, some gigantic number of entries in it, 24 times 24. But this is another way of understanding what's happening here, because just by taking these 4 elements and these 6 elements as the first row and first column, we actually, just by multiplying an element from this row and from this column, we can get any other element of U45 in a unique fashion. So every element of U45 can be uniquely written as a product of something from this subgroup and a product of something from that subgroup. Okay? So these subgroups are not only isomorphic to U5 and U9, but because of what else we know about those U groups, that means that this is isomorphic to Z4, and that the U9 subgroup is isomorphic to Z6. That means, for example, that each one of those has a generator. Right? In particular, let's say we could try 19. 19 is probably a generator for this one. And then this has got some generators in it also. Right, so you could identify, in fact, that's kind of nice, right? We could characterize everything in this group, U45, as some power of a generator up here multiplied by some power of one of these generators. So that also gives us this nice number theoretic bounty, right? Every x in U45 can uniquely be written in that form as x equals, so I'm not checking here that 19 is a generator, but let's say that 19 is one of my generators. And for Z6, let's say 31 is one of my generators for Z6, right? So what this would mean is that everything which is relatively prime to 45, that we can write it in one and only one way as a product of a power of 19 and a power of 31, taken mod 45, of course, as everything is here. Okay, so we have this way of understanding U45. To get us to our next topic, I want to pose the question, what are normal subgroups? Just as a reminder, how would I know, for example, that this green subgroup and this purple subgroup are normal in U45? What's the quick and dirty explanation? The left and right cosets of any given element have to equal one another. How do we know that's going to be the case in this group? Because this group is abelian. And therefore, left cosets and right cosets of any element are automatically equal to one another because the operation of the group commutes. So for sure, these are going to be normal subgroups. But I want to take that a step further. Why are normal subgroups important to us? Why do we care? We care about normal subgroups because those are the ones that we can build larger groups on top of, right? In order for this U45 to be built out of the green and the purple subgroups here, those subgroups need to be normal so that we can understand each one of them as representing the cosets of the other, for example, right? That gives us a powerful building block. If I have a subgroup that's not normal, I can't necessarily build the entire group on top of it, right? But subgroups that are normal form our building blocks. And so the question that we need to be able to reckon with, and this is the pivot, is where do normal subgroups come from? And I'm just going to use this opportunity to sort of give away my answer to this question, which has nothing to do with, you know, when a group and an operation love each other very much and they fall in love and they run away together and a stork flies in through the window with a normal subgroup. I would love it if that were the story. Maybe it is. But where do normal subgroups come from? They come from the best place to find normal subgroups. The best way to make normal subgroups is to make them with functions. But not just any kinds of functions. Namely, functions having the homomorphism property. When was the last time we thought about the homomorphism property?
2 weeks ago?
Several weeks ago, yeah. What was the topic? Isomorphisms, right. We first learned about isomorphisms, which are this really powerful tool to compare two groups that are, quote, the same, right? And every isomorphism meets 3 criteria. What are they? Yeah, I'm kind of thinking of bijection as being 2 separate components. But yeah, so on the one hand, we need this function to be a bijection, so it has to be both 1-to-1 and onto. And then what's the third thing? And the third thing is the homomorphism property. Remind me what the homomorphism property is?
It's like the multiplication thing.
Yeah, the multiplication thing. Phi of x, let's use x's and y's, let's say. Phi of xy is equal to phi of x times phi of y, where times means different things potentially in these two groups. But yeah, right, so that property.
Before we leave.
So this is kind of the metaphysical answer to our question. If we can make a function that's not necessarily an isomorphism, so it might not necessarily have the 1-to-1 and onto business going for it. But if it has the homomorphism property, then it turns out it will define a normal subgroup for us. And this is going to be an important tool for us to finish up.